Today we are going to continue our discussion of elemental properties, and we are going to talk briefly about energy levels of electrons, electron distribution, and electron orbitals. Before we begin our discussion of electron energy levels, it is important to set the premise by stating that atoms are mostly empty space. So, when two atoms approach each other in a chemical reaction, their nuclei don't come close enough together to interact. Only electrons are directly involved in chemical reactions because they are within a cloud around the nucleus, if we think back to the simplified model of an atom. An atom's electrons vary in the amount of potential energy they possess. Remember that potential energy is the energy that matter possesses because of its location or structure. If we remember this, electrons are negatively charged and thus are attracted to the nucleus, which is positively charged. So it is going to take work to move an electron farther and farther away from the nucleus, meaning that the more distant an electron is from the nucleus, the greater the potential energy it will possess. Changes in the potential energy of electrons can only occur in steps of fixed amounts, which is emphasized in the image of the staircase seen in the slide. An electron's potential energy is determined by its energy level, or electron shell, and an electron can only exist at certain energy levels, not between them. In the image to the right, we see that the electron shells can be depicted by concentric circles, where the first shell is the lowest in energy, and the energy gradually increases, expanding outward. An electron can move from one shell to another only by absorbing or losing an amount of energy equal to the difference in energy between the energy levels of the two shells. So, as we can see in the image, when an electron absorbs energy, it moves to a shell farther out from the nucleus, and when an electron loses energy, it falls back to a shell closer to the nucleus. Many times this energy presents itself in the form of heat, so heat would be needed to move the electron to an outer shell, or heat would be given off into the environment when an electron moves to an inner shell. Now that we've discussed electron shells briefly, we can continue our discussion with electron distribution and chemical properties. The chemical behavior of an atom depends mostly on the number of electrons in the outermost shell, the valence shell, and these electrons are called valence electrons. The periodic table of elements shows the electron distribution for each element, arranged in periods corresponding to the number of electron shells in their atoms. It is important to note that an atom with a complete valence shell, such as those in group 18, is unreactive and will not interact readily with other atoms. Now, although the concentric model of electron shells previously discussed is convenient for understanding, it has its flaws and does not generally give scientists a real picture of an atom. As a result, the scientists focus on the space where an electron spends most of its time to learn more, and over time called this space the orbital. Each electron shell was found to contain a specific number of orbitals associated with it, seen in the image to the right with neon as an example, and each orbital contained distinctive shapes and orientations. The first electron shell has only an s orbital that is spherical in shape. The second orbital has another spherical s orbital and 3 p orbitals that are each shaped somewhat like dumbbells, aligned along 3 orthogonal axes. The third and higher shells all contain s and p orbitals as well, but also consist of more complex orbitals and shapes. A key takeaway when discussing orbitals is that no more than 2 electrons can house a single orbital, emphasized by the Pauli exclusion principle. And as stated at the bottom of the slide, the reactivity of an atom arises from the presence of unpaired electrons in one or more orbitals of the atom's valence shell. We will see this more when we discuss chemical bonding, and we will notice that atoms interact in a way that completes their valence shells. This concludes the second part of this series. Elemental properties depend on the structure of its atoms. Thank you for watching, and have a great day.